Welcome back to ECE 442-542. Homework number 5 is due on the 1st of April. Oh, that's today. Homework number 5 is due today, as is deliverable number 1 if you're in 542 working on that project. You'll want to submit your deliverable number 1 into the appropriate drop box for that. Homework number 6 is due in a week, and in a few days we have our third exam, a week from Wednesday. And before that, there is a review session a week from today at 7 p.m. Hopefully we will have this space. And if you have questions or topics that you would like addressed during that review session, you can take the quiz or submit those via the quiz on D2L. There are, if you haven't been looking on D2L routinely, there are some supplements to Unit 5, and there will probably be supplements to Unit 6. We want to stay healthy, so we're taking our supplements. We have a lot of different supplements on Unit 5. Creating T sub C. These should have helped, I hope, in homework number 5. Competing specs. How do you trade these off if they aren't all consistent? Sampling and Nyquist. What's the connection there? An overview on controller. If you've never seen control design, that might be helpful. And even if you have, maybe that's a good summary. And then there's another example illustrating how you can use Ragazzini to design a controller. And it actually illustrates how brute force Ragazzini might give rise to some characteristics in your closed loop system that maybe aren't acceptable. And one of those is intersample ripple. And that's why we want to continue with other control strategies. And today we're going to talk about PID control design, and those are going to be examined through the use of a design technique called a root locus. And the root locus approach or analysis is in chapter 13 of the Shams book, and I've now scanned those, and you can find those on D2L either under course resources or in Unit 6 as a reading. Maybe I've put those at the very bottom of the Unit 6 page, but you should be able to see the analysis for the root locus, which is Chapter 13, and the design using root locus, which is Chapter 14. Our goals then today are to summarize a PID controller, and we'll start looking at the beginnings of that, and that is to look at one of those channels of controllers, which is the proportional control approach. It's just using one of the 3 pieces of a PID. So if you're talking about this in an interview, you may not want to say, oh yeah, we did PID control in 442 or 542. You might want to say PID. That will let you into the club in terms of talking about this as a controller design. We'll look at how we can approach proportional control and see that there may actually be limits on the gain, K, that you're using in your controller. What's the stability range? Maybe there's a range of values on K, and that will hopefully naturally lead us into this design approach and an analysis approach called a root locus approach. And that, if you've taken a classical controls class, the sketching of the root locus is exactly the same in this class. It's just we're in a different plane. We're in the Z plane instead of the S plane, and so the Z plane, you interpret these pole locations differently than in the S plane. In the S plane, we always wanted to be in the left half plane for stability. Now we want to be inside the unit circle for stability in the Z plane. So we want all of our branches of our root loci, all of the paths that these closed loop poles might follow as we adjust a parameter, we want all of those to be simultaneously inside the unit circle to guarantee stability. We will also see that all of these root locus properties that we might use to sketch the root locus arise from this one formula. It's really the denominator polynomial in a closed loop transfer function. 1 plus k g bar. G bar is not just the plant G. It could incorporate some additional pieces. It might have a derivative piece or some phase lead, phase lag piece, etc. That's why I'm calling it a G bar. But we pull out the adjustable gain K, and that's what we're manipulating to create these branches in the complex Z-plane. But knowing complex numbers and dealing with this complex plane says we want 1 plus k g bar of z to equal 0. We're really looking at what values of z in that complex plane satisfy that, and that leads to two conditions. A magnitude condition. If you solve that equation for k g bar, you see that it equals -1. And -1, we can say, oh, that has a magnitude of 1, and it has a phase angle of -180 degrees. Those are the two conditions that all of the root locus properties are derived from. And again, if you're looking to construct these root loci, that's chapter 13. If you want to see how they are used as a design tool, or the root locus as a design tool, you can look in chapter 14 that are available to you as a scanned version within D2L. Let's look at this PID controller. I won't slip again. How's that? So we have a proportional integral derivative controller, and conceptually it's not that hard. We have a proportional piece, an integral piece, and a derivative piece, and all of these pieces play with the air signal, where here we're defining that to be, we have a unity output feedback. The air signal is just comparing a reference input R to the measured output Y. Comparing just means we're subtracting Y from R. That generates an error. That error then is processed three different ways in parallel. One, you just take that error and scale it with a proportionality value, a gain, case of P. The other one, the middle one, you integrate that error. And the bottom one is you differentiate that error, scale it up, and you combine all three of those to form the input that drives your plant G of Z. The whole idea is that you can hopefully select the proportional, integral, and derivative pieces of this controller to give you more acceptable behavior in your closed loop system. That's the idea. You want to be able to adjust these different gains to make the closed loop what you want it to be, or more like what you want it to be. I'm going to just quickly show these three parts using a continuous time environment. In continuous time, the proportional piece, as I said, it just takes the error and scales it by some gain case of P. So and what's happening on the right-hand side is at the same time as what's happening on the left-hand side. The input now depends on the error now. The T is the same on both the right and the left. The proportional piece then works with the error at the present instant of time. That's one way of thinking about the proportional piece of this PID controller. Contrast that with these other two pieces. The integral piece, now we are integrating. If the error, whatever the error was for all time, we now integrate that as a function of time, and that could build up to a large value if your error was even small over a large interval of time. And then you scale that integrated air, and that now makes up your integral air piece. And what happens in that integral? Well, the current time is the upper limit on that integral, which means that you're using all previous air signals to influence this integral air term. The proportional just worked with the present value of the air. The integral piece works with all past values of the air. You're now integrating from minus infinity up to the present time. So your input piece from your integral term is dealing with past air values. Contrast that with the derivative term. The derivative term is sort of anticipating where you're thinking the air is going to go. You're differentiating the air. So what's the slope of the air at the present instant of time? And you're scaling that to create an influence on the input signal that you're applying to your plant. Each of these three pieces work with a different part of the air. The proportional piece is the current air, the air at the present time. The integral piece, past airs. The derivative piece, the anticipated or future. And I've tried to illustrate that here with this graphic showing as a function of time the air, and ideally you would like that air to be driving that air to zero. Remember what the air is. That's the difference between the reference where we probably want our system to go and the output of the system, which is where the system is actually going. And here I'm showing that the air over time is going down. And I've just drawn a line in the sand and said, oh, here's T sub 0. That's now. That's what the proportional gain would amplify or work with. The integral piece would be integrating all of that air signal from previous time up to now. And the derivative term is anticipating, based on the derivative of the air, the direction that that air is moving. And here's where the big bucks come with the trade-off. That's why they pay you the dollars that they pay you when you finish, is answering these or asking these or working your way through this trade-off. If you emphasize the integral piece, then maybe you're more worried about steady state accuracy. Are we locked on? Is Y tracking R? Or is there a very small difference between Y and where we're saying we want the reference signal, or where we're applying our reference signal? Or do we want the system to be responding quickly, speed of response? There's usually a trade-off between those two demands, speed of response or steady state accuracy. And you could say it a different way. You could say, oh, what's your steady state error? Is it 0? Is it small? And what's the transient? Maybe we're willing to trade off some speed, or maybe trade off some percent overshoot with better steady state error behavior. That's what you need to be thinking about when you're dealing with control and answering or designing controllers. How are we doing in the steady state? What's our error? And how did we get there? Are we okay with the way that we progressed to that final condition? Here are the PID beginnings, and I apologize for scrolling through this, but I know that you have notes and you can quickly, you just have this implanted in your brain, I know, this block diagram. You know G, that's the plant, and you don't even need your calculator to remember this. Right, Carter? Anyway, we have K, that's what we're focusing on now, is the proportional control. So now we have I didn't recognize you earlier. You looked different. It was out of context, wasn't it? Oh, is that what it was? Sunglasses. Yeah. When I see you somewhere else other than the classroom, you catch me off guard. I see you riding a bike on campus. Then maybe, oh, yes, I should know that person, right? Yeah. All right, so here we have our proportional control. I'm giving you time to sketch this if you hadn't already sketched it. You have it mentally. You have the plant, and right now today what we want to play with is just the one piece, the P piece, the PID. We just want to talk about the proportional piece and get a feel for that. What can we do with proportional control given some plant G of Z? And I hope that we can all at this point find the closed loop transfer function. Block diagram algebra allows us, and this is a cheer that we had last fall. I don't know that well, I guess, do they cheer for softball or baseball? Maybe they do. Maybe rugby, do they cheer for that? Maybe a little bit. I'm picking on someone today, I apologize, but hopefully we're okay with that. Here's our transfer function, kg over 1 plus kg. Somebody's going to get kg. CAG. Nah, never mind. kg over 1 plus kg. What influences the closed loop dynamics? If I gave you that closed loop transfer function and I said, what influences the dynamic behavior of that closed loop system, what would you point to? Or what would you come back with? You have kg over 1 plus kg. Is there anything there that gives you insight into how that system will behave in the closed loop? What influences the dynamics of that closed loop system? Any transfer function. If I just handed you a transfer function and I said, here's an h of z, and you were texting that to your friend, and good thing you're at home and you can't be called out, right, in class. So now you have a transfer function, h of z, and I say, how's it going to behave? What would you look at? You would look at the poles, wouldn't you? What influences the poles in this closed loop transfer function? The denominator, which is influenced by 1 plus kg of z. The dynamics of the closed loop system are governed by that expression, 1 plus kg of z. That's the denominator in t sub c of z, and you might hear me call it the closed loop characteristic polynomial. And we set that characteristic polynomial equal to 0 to obtain a characteristic equation, and the roots of that characteristic equation give us our poles. And in this case, give us our closed loop poles. What we want to do now is examine a particular plant where the plant now is given as g of z is 1 over z minus 2, and we want to look at that assuming we have proportional control being applied. If that's the case, what is our closed loop transfer function? Assuming the same block diagram that we had before, right there. Now we have a particular g of z. There's our closed loop transfer function. Let's just copy that down. That's now, in terms of these transfer functions, that's c of z, g of z, over 1 plus c of z, g of z. But c of z is now just proportional control, or now we have k times g of z over 1 plus k g of z. Substituting in the g, we have now k over z minus 2 over 1 plus k over z minus 2. And that might look a little odd since we have a ratio of ratios. Let's get everything over the same common denominator. And we can multiply by 1, which is z minus 2 over z minus 2, or we can just cancel the denominators in the numerator and denominator, and we're left now with t sub c of z equaling k over z minus 2 plus k. Everyone comfortable with that? Now we have k as an adjustable parameter, and what will our closed loop dynamics, or how will they be determined from this closed loop transfer function? What are our closed loop dynamics? Or what are the poles of the closed loop system? What did we just say they were? Or what would they be? If I handed you a transfer function, what would you pull out of that transfer function to give me the dynamics? I hope you're off in your own little world and you're not just completely lost with what I'm saying, which is kind of the clue I'm picking up from looking at your faces, but maybe it's just been a long day. What are the closed loop dynamics? What governs those? Or what equation do we want to look at? Want to look at the values of z that cause that denominator to vanish, don't we? Those are the closed loop dynamics, or we're now looking at z minus 2 plus k equaling 0, where this is now our closed loop polynomial, and this whole thing with the equal sign is the closed loop characteristic equation. Our goal, in fact, is to adjust this adjustable proportional gain k to locate the closed loop pole. We only have one. That's a first order polynomial. It's not a square. It's not a cube. We only have one pole that we're adjusting, and we have one parameter to do that adjusting with. That's the k. We want to adjust k to locate the closed loop pole at an acceptable location. And now that probably makes you feel uncomfortable when I say acceptable location. You go, well, what's acceptable to you? It might not be acceptable to someone else. And that's, again, why you're learning what might be acceptable or not. We need to now figure out what's going to be, and there may not be one right answer. There may be many right answers, depending on your definition of acceptable. What do you mean by acceptable? But in this case, we know that whatever we pick for k, it has to satisfy z minus 2 plus k equaling 0. Or we now have z minus 2 plus k equaling 0 tells us that whatever we pick for k, the pole is going to be located at 2 minus k. And in fact, we can get even maybe a better feel for that if we look at what this looks like, this value of z, what it looks like in the complex z-plane. If k is equal to 0, where's the pole? And when we started on this system, was our system stable or unstable in the open loop? Is g of z stable or unstable? It's unstable. That pole is outside the unit circle. It's located at z equal to 2, and that's where we better start if k is equal to 0. Let's say here's 1 and here's 2. If we had a pole at 2, that's the open loop pole location. And that's in fact where we are at when k is equal to 0. What happens when k is equal to 1/2? Where will we live in the complex z-plane? If k is equal to 1/2, you can just solve that z equation and say z is equal to 2 minus 1/2. This is heady math stuff, isn't it? I was talking, never mind, earlier about math, and I said algebra is very important. Well, we have an algebra problem. Now, if k is equal to 1/2, do you see that we would be at 3/2 for z? Is that a big enough k? Is that an acceptable location? Probably not if you want your closed loop system to be stable. What about if I now picked k equal to 3/2? Now what point would I be at? Now I would be here at 1/2. So when k is equal to 3/2, I've now moved inside the unit circle, and if I wanted to, if I could draw this, I might want to draw that unit circle just to give myself something to reference this choice of value k. As I adjust k, what's going to happen? What points will I map out? Or what will be the locus of poles in the complex z-plane? Where can I get to with this proportional controller as I move from k equal to 0, which is what happens here, and I just keep cranking up k? Do you see that I'm going to live on that real line, and the more I crank up k, the more to the left I'm going to move in terms of my pole location. And hopefully you can see that there's probably some acceptable region there that you might want to live in. Probably you want k to be living somewhere, and we'll talk about that in a minute, but let me just say that now you've sketched your first root locus. What we've sketched, this is now the locus of potential closed loop poles, assuming that we're allowing k to vary from 0 up to positive infinity. And I hope that you can say that, okay, well, one possibility for picking a gain k might be to do the following. We know that the characteristic polynomial is given by z minus 2 plus k. That's our characteristic polynomial. We could say, well, I want that to look like a desired closed loop polynomial or a particular polynomial, and that I might say is z minus 1/2. This is now where I would really like my closed loop polynomial to look like. This is now a desired closed loop polynomial, and you can make that happen by the appropriate choice of k. In general, when you're comparing a left side and a right side, again, just doing algebra, we're comparing the coefficients on all the powers of z, and in this case we compare the coefficient of z to the 1 and z to the 0. We just have two z coefficients. And so I'll just say equating coefficients between sides or on both sides of what we have, the closed loop polynomial, comparing that to the desired closed loop polynomial. What happens when we compare the coefficients that scale z? What's the coefficient of z on the left? It's a 1, isn't it? What's the coefficient on the right? 1. So that's trivial, this particular comparison, because that polynomial or those polynomials were both assumed to be monic, meaning they had a coefficient of 1. That's a trivial result. In general, we may have to compare all of the different coefficients. If we now look at z to the 0, on the left-hand side we see we have minus 2 plus k, and on the right-hand side we have minus 1/2. Or if we now add 2 to both sides, there's another way of coming up with that value of k equal to 3/2 being a valid or a reasonable gain value. With k equal to 3/2, the closed loop transfer function do you remember what it was structurally before? The t sub c of z, when we cleared all the denominator and numerator denominators, we ended up with k, which in this case was 3/2 in the numerator, over z minus 2 plus k, or this is now 3/2 over z minus 1/2. And what was our proportional controller to make this closed loop transfer function? We've now designed our first PID controller. It's fairly maybe trivial, but it's now just a proportional gain of 3/2. A PID controller with the I term and the D term set to 0, we have a proportional term. There's a PID controller that is 3/2. What observations can we make relative to this C of z equal to 3/2 and the result? One, C of z, does C of z being equal to 3/2, did that cancel any unstable poles or zeros in our original plant? No. So that's a good thing. C of z does not cancel any. It did make an unstable system stable, but it didn't cancel anything to make that happen. It just applied a gain. So C of z does not cancel any unstable pole or poles or unstable zeros. Here we know what unstable zeros are. Those are the values of 0 that are outside the unit circle to produce T sub c of z equaling 3/2 over z minus 1/2. We were also able to make the closed loop system as stable and we just have a single pole in our closed loop system. Closed loop system is stable with a single pole at z equal to 1/2. If we now have a closed loop pole at 1/2 and somebody energizes some energy storage element in this system, what's the natural response going to look like if we labeled that natural response as y of n? We're not applying any input. We just want to energize the system and say, okay, what happens? What's it going to look like? What's the initial condition response if in fact we have a closed loop system with a proportional gain and that gain is equal to 3/2? What's y of n going to look like structurally? Do we know? Is there any clue on the board? What's y of n look like? How does it shake? How does it move? If we know statement 2 is true, we have a closed loop system, it's stable, with a single pole at z equal to 1/2. What happens to our natural response? Its modes perform based on the poles. And we only have one, so we only have one mode. And it's shaking at 1/2, 1/2 to the n. So the structure of this, we could say, is alpha 1/2 to the n. And that might be an acceptable behavior for an initial condition response. What's our DC gain? See all of these questions or observations we can make if you were discussing this on a napkin somewhere, maybe multiple napkins, pull out a different, or even index cards. You could maybe even illustrate this with some index cards. Just saying, if you brought those along. We have a DC gain of our closed loop system, and what's that going to be? How do we find that? We know T sub c of z, we know our transfer function, we just evaluate that at dc, which is when z is equal to 1. Or we now have 3/2 over z minus 1/2 with z equal to 1. We have a DC gain of 3. Okay, let's investigate that a little bit. DC gain of 3. What happens, or what is our steady state error if somebody applies a unit step to our system? What's the steady state error to a unit step? What's the reference input at infinity, or at a big value of time, big N? If it's a unit step, what do we know the reference input needs to be? We know that's 1. What's the final value of our output going to be? We have our DC gain, which is 3, times 1. So we now have a final value of 3. This is due to our DC gain. Do we know that we're going there? Or how do we know that we're going there? Our system was stable, wasn't it? So we are going to settle at a final value. The final value will be 3. So now we have an error at infinity is r infinity minus y of infinity. That's how we defined our error. This is 1 minus 3. We have a steady state error of minus 2. Meaning, if you wanted to sketch that, if this is now time, here's our r equaling 1, and maybe this isn't drawn very accurately, but there's our output. What can we say out here? There's our error at infinity. That's our steady state error. I commanded the system to go to 1. Where did it go? 3. With what? A proportional controller. Is that okay? You wanted to go to Phoenix, but you ended up 3 times away, huh? Maybe, whatever that means. Maybe that's not what you wanted to do. So maybe we may need a different controller structure than a proportional controller. May need a different controller structure. Yeah, but we were stable. Yes, you were stable. You did stabilize. You did go to a final value. It's just maybe you're not accepting that steady state accuracy. In this case, the proportional control, the P and the PID, may not produce an acceptable steady state error. What about the transient response? What did it look like? Or what governed that exponential curve shape? That was the 1/2, wasn't it? The 1/2 to the n was what the transient response looked like. That may be acceptable. You now may have to worry about these competing objectives. You may have to trade them off. You may have to figure out, oh, can we reduce our error? Oh, do I want to change or modify my transient response? Question? So now what the question was, I think, was where did this error come from? I just drew it quickly, but what did I try to show? I tried to show that this is now y of infinity, which I calculated to be 3. That's the final value of my output y. And my error is then this blue dashed line is r at infinity. That was my reference input. Or this is now r of infinity minus y of infinity, which is 1 minus 3, or this is now minus 2. It's just how we've defined the error, and we now have an error saying that we're comparing the reference minus the output. And in that definition of the error, our error being minus 2 actually says that our output is 3, when our input is 1. Does that help? Yes, so it looks weird maybe. Why are we getting an error of -2 when we're bigger than our reference? But it's the way that we've defined the error. The reference minus the output, negative output feedback. Let's examine K a little bit more before we start worrying about adding an I or a D into our controller structure. Now let's just continue to work a little bit with the P. So let's examine adjusting K a little more. Or one could actually increase K to yield a different response. We could actually increase K to get or obtain a deadbeat response. Or if we do it by comparing polynomials, we know that z minus 2 plus k, that's our characteristic polynomial. We want that to be equal to, for a deadbeat response, what do we want the polynomial to look like on the right? If we exaggerate all or explicitly show all the information, it's z minus 0. We want to pole at 0. If that's the case, we know both of those are monic, and so the only information that we're going to have is by equating the constant coefficients, which now says we have minus 2 plus k equaling 0, or with k cranked up to 2, now we'll have a deadbeat response. And what's our controller look like? It's still just a gain. It's still just k, but now k is 2. And what's our closed loop transfer function now? It was k, which is 2 over z minus 2 plus k over z. What's the DC gain now? That's not too hard. 2 over 1. Can we solve that one? That's pretty easy. Now our DC gain is 2. Do you see that that was an improvement maybe if we wanted to reduce our steady state error. Now we have a steady state error of 1. We have a faster system. It's now deadbeat in behavior. It gets there in one step and it stays after one step. It doesn't do this exponential of 1/2, 1/2 squared, 1/2 cubed, etc. to get there. Well, if that's the case, if a little gets us that much, can a lot get us even better? Maybe not so much, huh? So is there a limit or a limiting value of k for stability? And I know you already have this answered, because you've sketched this either mentally or on your paper. Here's the z-plane. We started with a pole out here at 2. And what value of gain do we need to have our system stabilized? or where are we on the complex z-plane, to first stabilize our system by adjusting this knob that is adjusting k. We will need to crank up the gain to get us to that triangle. This will be our lower limit. On our z-plane location. And do you see that this would be our upper limit at -1? If we kept cranking up k, if we cranked up our k to get us to that -1 point, this would be our upper limit. In our z-plane location. And if we simply moved k from 0 all the way up to plus infinity, we could live anywhere on that real axis between 2 and minus infinity. This is, in fact, the root locus. And if we wanted to, we could calculate those k values, although we've already done that. Let's just go ahead and do it for completeness. For our lower case, we need to find what happens at the triangle. We have z minus 2 plus k equaling z minus 1. To make our system stable, we need to adjust that knob on k to be at least 1. It can't be 1/2. It would still be outside the unit circle. The upper limit, which was our box, says we have now z minus 2 plus k equaling z plus 1, or when the right-hand side would have a value of z when it vanished of -1. K is now 1 plus 2, or 3. And that was pretty easy. If somebody now said, oh, you have a knob, k, it goes from 0 to infinity, what are the ranges on that knob to maintain stability of your closed-loop system? You now know that you need to adjust that knob between 1 and 3 for stability. Let's now look at that root locus a little bit more generally. Here we found one with a first order system, a first order denominator, and it was pretty easy with just the adjusting of k. We zipped it all the way from where we started all the way to minus infinity by turning k or increasing k. A standard root locus is given by the roots of 1 plus k g bar of z equaling 0. As k is increased, from k equal to 0 to k going to infinity. That's the definition of a root locus. We just look at how the roots of 1 plus k g bar of z equaling 0, what those look like as we adjust k from 0 to infinity. And you could do that numerically. You could plug in k equal to 1/2. And let's say g bar of z was corresponding to a 10th order system. We would now have 10 branches in our complex z-plane, and for each value of k, we would be finding 10 roots of that equation. Let's look at a case that's maybe not quite that easy. I'll save the k equal 10 for an exam. Let's look at, okay, I've lost the entire class. I didn't get any response on that. Let's look at an example. I'm just going to pack up and go. They won't even know, right? So now, example 2. Suppose we have g of z equaling 1 over z, z minus 3/2. Is that system stable in the open loop? Is that an open loop stable system? No. Our poles are at 0 and at 3/2. We just need one pole outside the unit circle to cause everything to be unstable. Again, let's just focus for now on proportional control. Can we stabilize this system by a particular value of k or a range of k? That's the question. So is there, or do we have to introduce a more complicated controller structure? Is there a stabilizing value or range of stabilizing values for k? Again, how would you do this? Control engineer walks into a restaurant. Notice I didn't say somewhere else. Don't want to get in too much trouble. Can you stabilize that system with k? How would you figure that out? The reason we walked into a restaurant is maybe they have napkins, right? So now you can pull out a pen and start scribbling on that napkin. They usually have crayons and something at the restaurant to entertain somebody. Well, all we need is a napkin and a marker, right? We're engineers. So we start sketching g of z. You can sketch the pole zero diagram of that. You have two poles, one at the origin and one at 3/2, and you go, well, I don't know. That's where they are. But let's now think this through. How can we figure out where those poles might move as we adjust k? Where do they move in the complex plane when they start at 0 and 3/2? Let's now sketch a diagram. You're buying time. You're now at an interview. And they say, well, what happens if you apply proportional control to that system? G of z, 1 over z, z minus 3/2. And if you don't know, you don't say, oh, I took control from Tharp. You just leave that out of the conversation. You just go, you start thinking. So you say, well, let me draw the closed loop system, block diagram. You start showing that you do know some control concepts. What's that look like? Well, we have a gain k. We have our plant, g of z, and we're going to interconnect that in the classical way of just feeding back the output with a unity gain, comparing that with a reference signal, and that will then generate our output y. And again, you're buying time, so you can say, okay, we have this unity output feedback configuration, the closed loop transfer function, and if you really wanted to buy time, you could do the block diagram algebra. But you know this is just kg over 1 plus kg. So you write down, oh, the closed loop transfer function between the output y, between the input r, the reference input, and the output y is k g of z over 1 plus k g of z. That's if we're using proportional control. We now want to see or investigate stability by adjusting k. We're looking, is there a range of k for all roots? How many roots do we have in this system? 2. So we want both of those roots to be inside the unit circle simultaneously to maintain stability. Is there a location on that knob k as you adjust it from 0 to infinity that one might stabilize the system and maybe even give us a range of values? So we have a range of k for all roots of the closed loop polynomial giving rise to a closed loop characteristic equation. We want the roots of that, all values of z, to be inside the unit circle, to lie inside the unit circle. And we can do that by simply sketching the root locus. Here's what we'll do. The root locus of g of z is in fact determined by that equation, 1 plus k g of z equal to 0. Suppose we subtract 1 from both sides. We then have k g of z equaling minus 1. But we've played enough as electrical engineers to realize that minus 1, that's really a complex number. It has a magnitude of 1 at an angle that'll put us on the negative real axis, which is an angle of 180 or minus 180, and let's just all agree to call it minus 180 in this class. So now we have this could be rewritten as 1 at an angle of minus 180. Meaning, if k is greater than or equal to 0, we're not going to change the angle of kg of z. If k is greater than or equal to 0, then the angle of kg of z, that's just the angle on the left, has to equal the angle on the right. And what's the angle on the right? Minus 180. We're not changing it if k is positive or non-negative. So this is now the angle of g, which is now equal to minus 180 degrees. So we know that all points z that satisfy 1 plus k g of z equal to 0 must be such that the angle of g of z is equal to minus 180 to live on the root locus. Hopefully they're not throwing us out of the restaurant for using all of their napkins, but we've used quite a few. Now we're using another one. We're now drawing the z-plane. You just leave a big tip and they don't care at all, do they? So now what did we have? Where were our, well, let me label this. There's 1, 2, 3, 4. We're engineers. We don't tip that well, do we? Sorry, maybe we do. Prove me wrong, please. I might be waiting tables after this lecture, so maybe you can come into the restaurant that I'm working at. It wouldn't be my restaurant, but it would be one that I would be working at. All right, where were our open loop poles? Let's plot our pole zero diagram on the z-plane. If you're on an exam and I say sketch the root locus, if you want a few points out of several, the very first thing that you would want to do is plot the poles and the zeros on the z-plane of your transfer function in question. In this case, your transfer function is g of z. G of z was 1 over the quantity z times z minus 3/2, which had two poles. One was at the origin, and one was at 3/2. Those are our two poles. And now we want to find on this complex plane potential locations in the z-plane that live on the root locus. Not all points on the z-plane belong to the root locus. For this knob, as we adjust k, that's going to map out particular loci or paths that the closed loop poles belong to. That's the idea of the root locus. To get us thinking about this phase angle condition, let me draw a few points. I'm going to draw here, I'm going to get very creative. I'm going to draw a star. Whoa, a star. We had an unstable system on somebody's table, which means we had what? A pole outside the unit circle if we were in the discrete class, 542, 442. Let's say I have a star here. Let's say I have a box here. And what else? Oh, everything's in the cloud. So let me draw a cloud over here. Now, here's the question that I'm going to ask, and it's actually a three-part question. It's not a game show, but you can treat it that way. It's almost time for Jeopardy. Actually, it is time. So if you're at home, you probably have one screen that's playing Jeopardy and the other one you're listening to this and following us. Never mind. So you're watching which points and we have three. We have star. I knew I couldn't duplicate a star. We have a box. And we have a cloud. Which points lie on the root locus? Or do any of those points lie on the root locus? That's what we want to try to determine. We know g of z. It's 1 over the product of z with z minus 3/2. But g of z for any point z is just a complex number. And that complex number has a magnitude and an angle. If we look at g of z in general, we might have a polynomial in the numerator and a polynomial in the denominator. Now we just have a polynomial in the denominator. What's the angle of the numerator? If 1 is a complex number, what's the angle of 1? 0. So we have 1, we could say it has a magnitude of 1 and an angle of 0. So we really don't need to worry about the angle associated with the numerator in this particular g of z. Suppose we now want to look at the angle of g of z when z is over there at the star. And now if you're playing along at home, you may want to get up and start visualizing this z-plane on the floor and standing on the different pole locations. This phase angle of g of z is really going to be the angle of the zeros minus well, here maybe what I should say is the sum of the angles of our zeros minus the sum of the angles of our poles. Why do they subtract? If you think of each of these factors, you have zero factors and pole factors. Each of these factors have a magnitude and an angle. And what happens when you compare angles or try to find the net angle of G? You just add and subtract. If they're in the numerator, they add. If they're in the denominator, you're subtracting because they're downstairs. We just said that we have no zeros in this G of Z. So here we could say, oh, the contribution of the zeros is really nothing. I'm just going to leave sort of a placeholder so that you know that they're there. And now what we want to do is we want to look at the angle associated with the pole at each of these locations. Suppose you're standing on the pole at 3/2 and you're looking towards star. And angles are measured relative to a positive real line extending, the real line extending in the positive real direction, measured relative to that in a counterclockwise direction. I'm standing at 3/2 on the pole and I look towards the star. What angle am I having to look to see the star? 0. Is everybody okay with that? What if I move to the origin and I look to the star? What's my angle? 0. So now, relative to this point, I can now say that this is 0 degrees plus 0 degrees. And I have nothing, which is contributed by the zero factors, minus nothing. And what do I want that angle to be if I want that star to belong to the root locus or live on the root locus? What was that angle supposed to be? The angle of G needs to be minus 180 on the root locus. Is star on the root locus according to this? No. So we can emphatically answer this. Whoops. Doing more than that. I'm opening up all sorts of windows. I can say this is no. So let's do that again. Let's look at, not at the star, but let's look at G of Z when Z is equal to the box. What are the angles of the zeros? I still don't have any zeros, so that's nothing. But I'm going to leave the placeholder here just so that you know you do have to include that. And now this gets a little interesting. Now I'm standing at the 3/2 on the X, the pole, and what angle do I need to look through to see the box? You have to get up and do this at home. So now what are you doing? What angle are you looking through? My positive real axis is my right arm, and I'm looking through my left arm, and I'm swinging back to some very smiling faces. And what do I see? The box. What's the angle between my two arms? 180 degrees. You'll never forget how to find angles associated with poles, I hope. So now you have minus 180 degrees. What about now I move to the origin, the pole at z equal to 0, and I look at the box? What angle am I looking through? 0. Didn't have to break my back to do that one. Bend my back or whatever. I have to go somewhere to get work done now. But now what's the angle? Is that point on the root locus? Yes. What about if we looked at g of z, we'll do this fast, at the cloud? Oh no. What happens? I stand at 3/2 and I need to look at the cloud. 180. I'm standing at the origin and I need to look at the cloud. 180. I sum up two 180s and I get 360. I'm not going to do that unless I add them in components. I now end up at nothing minus 180 plus 180 equaling minus 360, which is the same as 0. That point is not on the root locus. What we now need to figure out is that, in fact, any point between these two would belong to the root locus. These two poles are going to move together, they're going to break away and go up there, and that's going to be our root locus diagram for this two-pole system. And we'll pick up at that point next time.